Mark, yes? Quick question, quick answer. No, well, we'll talk about it in a minute. How about that? Get it? Climate. I know, right? I told you it wasn't going to be that good, but okay, anyway. Or maybe there was a pun intended. I don't know. All right. 7 and 39. So here we go, ladies and gentlemen. We are going to get started, which means I need you to be quiet. So my plan for the day, I wanted to tell you what we're doing. So yesterday, and then we will answer 7 and 39, I promise. Yesterday, we defined energy a bunch. Oh, you can't see this. There you go. We defined energy a bunch. We talked about it, and we talked about these 3 kinds of energy that we're going to do, and we're going to define, and we're going to get to know really well. So today, we're going to define 2 of them. We're going to work with them. We're going to do some problem solving. Tomorrow, we will define the 3rd through a lab, and then we will do a little more problem solving. It's just going to kind of chew things together a little bit. And then next week, we'll do a couple more hands-on things as well. But today is going to be mostly calculation. You will certainly need a calculator, so you might want to get that out now if you don't have one, just so that you don't have to get up later. At the end of the day yesterday, right before the bell rang, we had like 6 minutes. You guys were like, we can't do something in 6 minutes. I was like, yes, we can. And if you remember, we defined gravitational potential energy. We said that gravitational potential energy is energy that an object has due to its position relative to the ground. Okay? Due to its position relative to the ground. So we set wherever ground is, and then if we lift something up, like a cheeseburger, right? We are doing work on it. This is where we were at. I just want to remind you because this is going to be relevant to the problems that we're going to work on. We do work on it by applying a force over a distance. The force we apply is equal to that of its weight, okay, the m times g. And we lift it a certain distance, d, but it's always in the upwards direction, right? Because we're talking about its position relative to the ground upwards. So often we will change that d to an h for height. And then we'll say that potential energy, gravitational potential energy is equal to mgh relative to some 0 point. Okay. We didn't actually plug any numbers in, so let's just make sure that we understand this and we understand where the units are coming from, and then we'll do those problems, okay? So here we go. If we say, so we got the mass, and mass is measured in kilograms, and we've got G. The book said that you could use 10. I wouldn't use 10. I did, I guess, on that one problem because it said so, but G is going to be that negative 9.8, right? I'm not going to use the negative sign, actually. Were you just about to say that? Wait, what about the negative? We're going to ignore the negative for now. We'll talk about what that means in a minute. That's meters per second squared. Everybody good with that? And then H is going to be measured in what kind of units do you think? It is height, measured in meters. So gravitational potential energy, this is just units down here, just to make this really clear what we're doing here, okay? So we've got kilograms times meter per second squared times meter. That is a lot to say. I don't really want to measure. Can you guys see if I'm sitting here? Is that okay? If you want to move for today, like even to the back or wherever you want to move, if that would be more helpful, please feel free to do that. Question. Answer.
Mg is multiplied. What is that H doing over there?
There just wasn't a lot of space. Does that make sense? We're multiplying them. Yeah. It was just because I wrote that 9.81, which was kind of annoying. It was wide, so that's, yeah. Totally fair question. I have 7 kilogram meter per second squared times meters. That doesn't sound like a very fun unit to say. Let's fix it. Help me out. Yeah, you could do something. I'm not sure. Couldn't you do? Yes, there's a in there. All right. You could. So option 1 is to cancel out those meters. So you've got kilograms.
Oh my gosh, was I actually right?
No, you can't. I'm sorry, you can't cancel them. You can square them. So it's going to be kilogram meters squared per second squared. That would be option 1. That doesn't sound pleasant. Let's see if there's another better option. Just because I wrote it down? Sure. So yes, we're getting there, but tell me why we're getting there, not just because Carbling wrote it down that way. Not trying to put you on the spot. Huh? Oh, okay. Tell me the answer to the question.
Because joules is also influenced by that.
Why, though? I want to know why. Because somebody thought it would be a great idea. No, that's the wrong answer.
Well, let's look at our numbers.
All right. Go, Niam.
Joule is a Newton meter.
Yeah, and that is a meter.
Hold on. Let go, Niam.
Isn't it because we already wrote that work is equal to the
Force times the distance.
Okay, we said the work energy theorem, right? We said that work was equal to change in energy. And so if work is in joules, that means energy has to be in joules. Is that what you're saying? Okay. Seems like a reasonable statement. Option 3. I changed my mind.
Force times the distance is also work and work. You got like an
What is a kilogram times meter per second squared? What have we taken a mass times an acceleration? What is a mass times an acceleration? It's a force. And what is a force measured in, guys? A Newton.
yeah, force times.
And a Newton times a meter is what? Yeah, but you were there, but you hadn't gotten there yet. You were here. I'm totally down with that, but I hadn't gotten this from you yet. That's what I was looking for. Yeah. Or you can call it Newton meters.
Yeah.
And if that makes you happier, by all means. By all means. Regardless, the thing that I want you to get from this experience, this wonderful conversation that we've just all been a part of, is that work and energy are measured in, you can fill in the blank. I'm going to write the word joules down. But if you would prefer to write the phrase Newton meters down, you are also welcome to do that. If you would like to write the phrase kilogram meter squared per second squared there, you can. That's not wrong. If you would like to write the phrase kilogram meter per second squared times meters down, you can. That's not wrong either. I'm going to write down joules because that seems easiest. Okay. All right. Are we okay? Sweet. Okay. So now that we know that, number 7, you said you want to go over? Okay, let's do 7 first. Sure, why not? Let's just do them all. Number 7. All right. Says if you do 100 joules of work to elevate a bucket of water, what is its gravitational potential energy relative to its starting point? So we know that the work is equal to the change in energy, right? That's that work energy rule, work energy, scary word insert here, theorem, right? Whatever you want to call it, okay? We're saying that we did 100 joules of work, and that's equal to the change in energy. And it says, what is its gravitational potential energy relative to its starting point? So let's call it starting point 0, right? And then we can say it's got 100 joules of potential energy. Is that okay? You shouldn't feel dumb. You should say, oh, that was something I hadn't quite got yet, but now I get it. Good for me. Yay for learning. It's a beautiful thing. That was part A. Part B said, oh, this is interesting. So B says now, what would the gravitational potential energy be if the bucket were raised twice as high? Twice the answer. The answer was 100, so we're going to say 200, right? So just to kind of make sure this really makes sense, we could say work is equal to change in energy, which is equal to m times g times h, right? So that was our 100 joules. But if we're gonna multiply that by 2, right? H times 2, I'm gonna multiply this by 2 as well, so it's gonna give you 200 joules. It's because we did it in the last 5 minutes of class yesterday. We haven't practiced with it. By the end of the day today, you should be all right. Deal? Okay. All right. How are we doing? Number what next? 38. Here we go. How many joules of potential energy does a 1 kilogram book gain when it's elevated 4 meters? When it's elevated 8 meters? So, how much potential energy does it gain? So we're talking about the change in potential energy, right? Is equal to, so we can write this down one way or the other, right? We can say it's m times g times the thing we're going to change is h. Or we can say that we can ask the work. It's the same problem either way, you guys. The mass of the book is 1 kilogram. This problem says to use g as 10. That kind of makes my heart sink a little bit. But you can use 10, I suppose, in this problem. And we're going to lift it up 4 meters. Is that okay? What's that? Yep. 40 what? 40 joules. 40 Newton meters. 40 kilogram meters squared per second squared. You know.
So the second one would be 80 then?
Ah, what's the question? When it's elevated 8? Yeah. Fair enough? Is that okay? Issues, questions, concerns? Go. Then that's perfectly lovely, and I would prefer that. In fact, I only did it this way because they told me to, but so you're going to get something, what, like 39 point something something? That's fine. That's totally lovely. Yep. Last one was number 39. Speaking of 39s, calculate the increase in potential energy when a 20 kilogram block of ice is lifted a vertical distance of 2 meters. Same question? Yeah? Change in potential energy is the way that they worded it. M times G times the change in H. So that's what, 20? That's a big block of ice. So then again, you can either use 10 or you can use 9.8. My answer on the sheet used 10 because I was being super lazy. So it's going to be something approximately 400, right? Because it's 20 times 10, which is 200 times 2, which is 400, or 390 something something. How's it going? Is that making sense? Sweet. Okay. So that practice is going to lead us into a really fairly simple conversation here for this next problem, but it's going to lead us to an important concept that I really want to make sure you understand. So I do not mind at all. That is absolutely fine. Okay, hold on just a second. I'm going to make this, draw this out a little bit. All right. I usually have a meter stick up here, but you're going to have to trust me. Here's my frog. Here he is. He's 0.65 meters above the table. Can you calculate his potential energy? 0.6. Yeah, you know. Do it. I'm guessing you can. I'm guessing it's almost exactly the same as the problems that you just did. So go ahead and do this. This is no. No, don't do it. How much potential energy does he have? We got this, right? Do we use 9.8 or 9.81? Okay, I can never remember. I'm sorry. My physical science class does the opposite, and so I can never remember which one is for which thing. Is that easy enough?
Mm-hmm.
Yay, multiplication. Maddie's gonna be sad she missed today. It's just like an all computation day. No ranking tasks even. Jeez.
Wow.
I know.
Oh, man.
I'll get some more tomorrow, don't worry. What you got?
3.83.
3.83. How we doing? Yeah?
Yep.
Units? Joules. Awesome. Let's do another one. Or blah, 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 blah. All right, so here's the next question. How much gravitational potential energy does he have when he's lifted 0.85 meters above the table? Same question. Right? This is easy. You got this. Maddie's not here, so I'll just say it because she would. And then she's going to make it hard. She doesn't talk like that high pitched, but we'll pretend like she does. What do we get? 5. Okay. Yay for multiplication?
Yeah.
Sweet. All right. Next question. How much work was done in lifting the frog from 0.65 meters above the table to 0.85 meters above the table? So I want you to figure it out. You can talk at your tables, and then we'll talk about it as a big group. But I want you to see if you can do it. That's okay. That was loud.
I know.
Jeez.
Okay.
So, how much work do you got 4 times distance?
Wait, are they parallel now?
Yeah.
Isn't that one?
Parallel to
Yes. So the distance is. Wait, which one are? Yeah, are we doing the?
Bottom one. How much work is done in lifting the frog from 0.65 to 0.85? Let me say it that way.
No, that's just
Oh,
it.
the whole thing.
Oh, wait, you're right. Oh my
Yeah.
What is the force?
Dylan, you gotta make it real complicated and start finding it.
Yeah.
Look smart. I got it. See, that's like a tricky
So that
question.
would be.
You have-
Wait.
Huh, they disguised it.
Are you calling me you're saying I'm asking a tricky question? What?
They were disguising it. Don't do.
Yes.
We figured out the answer.
You figured out the answer? You got that answer too?
Oh, yeah.
All right. Oh, yeah. All right. How much work was done? How much work was done, Dylan?
1.18.
1.18?
Wait a second.
You're
That's
right.
wrong because it's.
Oh,
it's
I don't get
from the- It's from the bottom to the up. You can't just.
It's from 65 to 85.
So that would be 0.2.
Mm-hmm.
And then you multiply by 0.6.
Dylan.
Did you not multiply?
No, then
by
you-
21?
You take the, it's,
You don't
work equals the
multiply by
change
9.
in energy. You take the final minus initial.
I thought you
The
just.
initial is the 3.8.
The work done is force times distance.
So the force of the frog is.
I give up on life.
Okay, but work also
like it when I
equals
make-
change in energy, and that determine the energy in both of them.
What's the mass of the frog? Right? Mass times.
What'd you guys get?
That's what I got.
1.17.
Yeah, that's what I also thought.
Yeah.
That means we're outvoted.
That doesn't necessarily mean you're wrong.
How did we get that?
Yeah,
I think
I'm
I'm
right.
doing fine.
How did you guys get what you're getting?
We
Work-
got.
Is
What did you get? What answer did you get?
1 or 0.12.
0.12? Okay. Okay, now keep talking. I just wanted to know what the number was.
We did how much work is done in lifting the frog is work done is force times distance. The distance from 0.65 to 0.85 is 0.2. Times that by the force, which is the weight of the frog, so 0.6 times 0.2 is 0.12.
Hmm.
But you have to multiply
By
force weight.
9.81.
Nine.
Okay.
Yeah, forces are
Our force is mass.
So multiply your answer by 9.81. Okay, so there was a little bit of discrepancy that was going on, and I'm not quite sure. There's very confused, very confused. All right, Abdul, why don't you tell us what you did? Well, how did you solve? Sweet. What did you do? How did you get your answer? Oh, that's not the right answer.
I think we did like, we were thinking about work, we did like 5 minus 3.83.
Okay, hold on. Say that again. You did 5 minus 3.83. So hold on. Let's figure out where in the world that came from. Oh, I'm frozen. There, is that better? Okay, so where did the 5 come from?
We calculated potential energy, we calculated
So that's the final potential energy,
that's the initial.
and this is the initial potential energy, yeah? And you subtracted them, and you got 1.17, 1.18, something like that.
Geez, that's so much easier.
Oh, and so why in the world did you subtract those things?
Because isn't it, what was the work done lifting the frog, so we thought like lifting it from 0.65 to 0.85. We thought that was the point where you said, we didn't.
No, you're not wrong. You're not wrong.
We didn't.
It just came to me. It just was like,
Yeah, you're
did you guys do it this way? Why did you subtract?
ready.
Say that loud. Did you hear that? That's why you did it.
Yes, that is why.
Work equals the change in energy, right? Work equals the change in energy. Now, did you guys do that too? Okay, but Tatum, you're upset. I don't know.
understand why
But I want to know what you did.
we just didn't multiply.
No. You got the right answer. Tell me how you got the right answer. Mm-hmm.
So we did like the long way.
That's okay. Keep telling me what you did.
So
So the force was,
2 times 9.81 times 0.6.
okay, so you did the mass times the acceleration of gravity, right? That's the force, times the change in distance of the height. You guys with me there? Okay. And you got the same thing, didn't you?
Yeah, so that's just 0.85 minus 0.65.
Yeah. The whole purpose of this, part of it was to get you to a little bit because it's fun, but also to make sure that you recognize that you can find potential energy in multiple ways, okay? Work equals the change in potential energy or the change in any energy, and you also know that gravitational potential energy equals mgh. Either one of those will work. Sometimes one is easier than the other. In this case, based on Tatum's reaction, I would say that this one must have been a little easier, right? Since she was like, oh, I should have done that. But is one wrong? No, they're both right. Okay. Okay, so here's my next question. I don't have my meter stick out, so we're just going to have to trust me that this is 0.65 meters above the table, okay? So I lift it from here to here. I've done work, yeah? Okay, now I want you to tell me what its potential energy is here.
It's the same, because if you drop it either way, it's gonna land the same way.
What is the distance?
No, it's just coming up with
Are you about the
Oh,
way
like on
you're
the
moving
floor?
it horizontally?
I am like a, oh man. Right, like a pizza.
Right, I would say, wouldn't it be?
Okay, so does the frog have potential energy right now?
Yeah.
Yes. If this is 0.65 meters, how much potential energy does he have?
3.83.
Yeah. Okay. I'm going to move him over here. How much potential energy does he have? I just walked him like this.
But it's a different. I feel like this is a
No, because it's different because like
It's an
it
interesting
increases
answer.
because the distance increases.
Say again?
Didn't it increase because the distance is gonna drop?
I'd agree with that
What's the
because,
height of your desk?
I don't know.
well, if you look at this on there from 0.85, that's already 2 joules higher. Basically 2.
So the height of my desk is 90.5 centimeters. So can you calculate his potential energy here? It was 90.5 to here. Plus 65, right? I'm doing centimeters. Right? Yeah, so 0.95 plus 0.65.
So it's 1.6.
So it's 1.6 for the height.
4? That's so easy, right?
So how much energy does he have now?
Yeah, 9.4.
Yeah, I
So
got
here's my table. There's my frog. This was what? 0.65. And now it's over here. And this is same. No, that wasn't supposed to be the same. That's supposed to be the same height. Make the frog a little bigger. There we go. And the floor is down here. And this height is what? 1.6. And you told me that when he was over the table, it was how much? 3.83 joules. And how much do you say he has now? Does that bother anybody?
I feel like it should.
I
don't get why it's increasing.
Say again.
I don't get why it's increasing because we only moved it horizontally, like not vertically.
That's right. It doesn't make sense. That should cause you issue, right? So here's my frog.
But there's it's like a different distance.
It's a different reference.
Yeah, different reference point.
Right.
So it's like
We
as
said
if we were moving it vertically.
the
'Cause if we
only
stayed on
way
it-
that we can change energy is by doing what?
Work.
Work. You with me there? If I hold the frog here and then I move him over here, have I done any work?
Or work has to be done.
It's perpendicular.
I'm applying a force this way and I'm changing distance this way. So did I do work? No work has been done. No work has been done. It's just like Janelle with her pizza, right? Yeah, my left arm's getting in there. Yeah. Janelle and her pizza say, no work is being done when I walk it across, right? So how in the world do I have one energy here and one energy here? The answer was, somebody said, Ian, what'd you say? A different reference point, a different height equals 0. Okay? Does that make sense? A different height equals 0. This is a kind of an important concept here. So we're changing our reference point. Reference, let me show you again. At the table, we say h equals 0 here. At the floor, we're saying h equals 0 here. Really, no work has been done. Really, so this is alternate reality. I would say that the energy here is still 3.83 joules. I would say the height is still equal to 0 here. And then what would we say about its energy down here? Like negative. It would have negative potential energy relative to that 0 point. If it has positive potential energy above, it has negative potential energy down below. Does that make sense? Okay. So here's the thing that I want you to remember about this. We're not going to go into we're not going to have to go through and calculate it all. Sometimes I do that, but not today. The thing that I want you to know for sure, okay, is that you can set h equals 0 wherever you want to. It is up to you. we could all do the same problem and we could have 14 different h equals 0 points. There are sometimes more logical choices, right? Like when I'm holding the frog over the table is a logical h equals 0 point. But somebody could pick h equals 0 to be the floor, and somebody could pick h equals 0 to be the floor on the first floor, right? If I take my frog and I just walk him straight across and I stick him out the window, I still haven't done any work, but now his h is a whole lot bigger relative to the ground. Are you with me there? Okay, so you just have to make sure that you set h equals 0, and then, this is the important part, you must stay consistent. Because if you're not consistent, then this weird stuff happens, where you're changing the amount of energy something has, even though no work has been done. The only way something can gain energy is if work has been done. Holla, you okay? Okay. All right. I'm going to move on if that's okay with everybody. Yeah, yeah. Sweet. I am not going to derive the next one. I'm just going to tell it to you because I want to make sure we get a chance to use it. The next energy that I want to talk about is kinetic. Kinetic energy is the energy of movement or motion. Yeah. If something is moving, it has kinetic energy. Can an object have both kinetic and potential energy, gravitational potential energy? Absolutely. If you set h equals 0 down here and I throw the frog, while he's being thrown, he's got some height and he's got some kinetic energy, yeah? Yeah. If something has to be moving, then it has to have a non-zero what that we've defined before. Starts with a V. Velocity. It has to have some non-zero velocity. And that's helpful in telling us what the equation is for kinetic energy. Bless you. Kinetic energy is going to be marked Ke and is equal to 1/2 of the mass times the velocity of the object squared. That's another big one we're going to put a box around. The 1/2 comes out of a like the rules for from kinematics. You can derive it from kinematics. We're not going to do that today, but I just want to make sure you know that there's a 1/2 in there. And then we're going to do a problem with it in a second. I'm just going to write this down. All right. But let's look at the units, because I want to make sure the units work out, because it'd be bad if I was telling you incorrect stuff, wouldn't it? Yeah. Mass. What's the unit for mass? Kilograms. What's the unit for velocity? Meters per second. But what are we doing to that meters per second? We're squaring it. If you square the number, you have to square the units as well, right? Everybody's favorite unit, here it comes, kilogram meters squared per second squared. Do you recognize that? Did you see that about 25 minutes ago? You now know, like that anytime you see kilogram meters squared per second squared, that's really just a joule or a Newton meter, right? All these things. So it is a joule. Life is good. Okay. Can I throw an example at you? Two of them, in fact. We'll do one at a time.
I did one.
One page of examples. Deal with it. All right, how much kinetic energy does my frog have if his velocity is 4 meters per second? You got this, right? Givens, 0.06 kilograms. V equals 4.0 meters per second. KE equals 1/2 mv squared. The biggest thing that people miss on this, anybody want to give it a guess? I was gonna say order of operations. Well, no doubt, yeah, but order of operations is part of it too. Yeah. What do I have to do to that point, or that 4? I have to square it. Which comes first, the squaring or the multiplicationing? Multiplicationing, I just said a really new word. Yes, the multiplying. That's right. So we have square first, right? Square first, then multiply and divide? What do we get?
Oh, I got it right.
4.8, is that what you said?
Yeah.
Sweet. Are other people in agreement with that?
Yeah.
Yeah? Did you square your 4 first?
Yeah. Yeah, I squared it first and then which was 16 and then multiplied it by 0.6
Mm-hmm.
and then I multiplied it by 0.5.
Hmm.
I got 5.
Might want to stick, is your
I'll try it again.
calculator in degree?
It doesn't matter for this one. All right, take a look at the second one.
Oh, man.
I don't like this.
Oh, wait, do it.
So that is,
Oh, it's because it's 0.60. That's fine.
Sorry.
No, that's okay. That's an easy fix. We got that.
you have to put a 0.60 at the end. I think
No, she had accidentally written 0.66 instead of 0.60. Does that make sense? Yeah. All right. I'm going to write out my givens here because I think it's going to be helpful. M is 670 kilograms. Kinetic energy is, that's 40000. That's a lot of zeros. We don't know the velocity. That's our question mark. Algebra. Doop-a-doop-a-doo, ba-doop-a-doop-a-doo. Did you like my song? I thought you would. That's why I did it. All right, let's do it. I help you. We want to get V all by itself, don't we? We got this. I need to get V all by itself. What do I need to get rid of?
Wait, let's just try this and see if
In the end, first one.
How do I get rid of a half?
Or you don't use either.
You could divide by a half or multiply by 2. Same. Yeah. Do you have a gray? I had a student who used to like follow along with like every color that I did. It was really cute.
I usually do, but I lost my green marker.
I'm sorry. Now what happens? Divide by mass?
Oh, shoot, I forgot it was velocity.
Yeah, this is why we're doing this, right? Yeah.
I bought multiple sets. Or that set. I bought a big set and then I had a little set before. So technically, these are the same, but this is a different set. These are yards. This big part.
Either day.
You guys are hilarious. I'm writing a lot of stuff down because I was watching the clock.
I got 10.92.
4. 4 times 10 to the 4th.
Oh, I didn't.
Did you get 10.97?
I don't know.
I did. Thank
Yeah.
goodness.
10 point what? 927?
Yes,
Yeah.
That's what I got.
After I had square root.
I did
Square root. That's right.
I did a different one, but I got
I was like, that's a fast velocity, 119.
That is a fast velocity.
I thought it was you. Wait,
And then I
you was you.
this cover that I have to try out one of the-
Hold on just a second.
How do you like that
You know,
pencil
he
pouch?
lost
It looks beautiful.
I love to feel it.
I know.
You guys are really funny. I think it's hilarious.
Using a makeup bag.
I love this one. I got it for its manufacturer, but I got it when I was in office.
Or you might do it subscription more than you do.
I have to get one.
I'm gonna pretend like
I
that.
think I got it at Target.
No, because someone had like the little pink one.
Oh, yeah.
Okay. Are we okay with this? Sweet. We've got a couple more minutes. I'm going to adjust your homework real quick, and then I'll do one of them with you because they are ranking tasks, most of them. I know, so we'll do one of them together, and then you want to do it for homework.
There was no ranking test today.
In class. I forgot that we had ranking tests for homework. Well, I don't have to help you.
We have another problem.
Why are you adding?
I'm changing it because
Oh, did we have 26 assigned yesterday?
26 was yesterday, yeah, which is why we're doing it today.
I already wrote all my homework down in my planner.
Oh, well, you should know better than that.
Well, I really want to be
Great
great.
investment for this class to get us a class-wide help.
You can get it.
My mom loves pens. I love pens.
I'm an obsession.
I saw these and became obsessed.
I've never seen my mom use a pencil.
Okay,
That's why you gotta get.
so I made it. It's fine. Actually, you had 4 problems, and I only have 3 now to do. I think. Right, hold on. Let me make sure I didn't mess that up. 28.
No, I'm good with this.
What do you want?
No, I want you to try 28. I think you can do it. I think you can do it. Then I think we're good.
No.
Then you want to have more later. It's better this way. So did you want to look at one together or no?
Can we just be done? I'm really.
I'm fine. It doesn't matter to me. You have to do your homework regardless.
Why are the lights off?
Because the people that were in here at the beginning said they didn't want them to turn on.
Like, I was like, they're just kind of having.
They're adults.